So my talk today is going to, in Sandra's words, raise the performance issue. I'm going to be telling you about transformations for high performance, in particular in optimizing compilers. Before I forget, I want to mention that when I get to the part of my talk where I talk about tiling transformation, this is joint work with a hierarchical tiling group at UCSD. It's jointly led with Larry Carter, and the students involved are Karen Hogstead, Nick Mitchell, Beth Simon, and Michelle Mills-Strout. And I particularly want to mention the latter two because they're actually here at Hopper. So the first question I asked myself when I was asked to be in this theory to practice session is, what am I doing here? So one answer is that, like many people, I started out in theory, in particular mathematical logic and complexity theory, and moved to what's considered a more practical area, namely optimizing compilers. Another answer is that I've actually, in the field of optimizing compilers, done what we might consider to be theory of compilers. That is, I've worked on intermediate representations, such as the program dependence graph or static single assignment form, and the corresponding kinds of transformations one does on that intermediate representation. And fortunately, a lot of that work has actually made it into real compilers. So that's an example of theory influencing practice. So what I'd like to tell you about today really is to weave those two themes together in the field of optimizing compilers. That is to show you how theory influences practice and vice versa, and give you some examples of that. So here we are in the world of optimizing compilers. And here we start out with a high-level language program and perform multiple transformations of that program with the aim of getting, hopefully, a faster program, a high-performance program. Okay? And those transforms are generally guided by some model of what the cost is, okay, of actually running, getting a faster program. And the ultimate test, of course, is to actually take your program and run it and see, is it in fact faster? Does it execute faster? So even here, there's a theory and a practice going on. Because the optimizing compiler is actually being guided by a model of what's taking place, it's in some sense working on theory, and the real practice is run that program and see how it goes. So here's the outline for my talk. We're going to start out with a particular aspect of the theory of compilers. It's almost a folklore in some sense. And we'll start out with the notion of transformation and the fact that transformations can actually influence each other. That is, they can help or hurt in terms of achieving the final goal. But then we're going to see that in practice, what compiler writers actually do is ignore that and pick some order to perform transformations. They may repeat transformations, but actually build into the compiler this order of performing the transformations and hope for the best. That is, you get good performance. However, the world is changing, and one of the changes is architectures are becoming more complex. Okay? And that change in practice is actually leading us to take a look back at that original assumption and form some new theory in which we're forced to actually take interactions of transformations into account. Okay? And hopefully that, again, will lead to better practice and so forth. So we're starting from theory, this theory that transformations actually interact. Here's an example. Constant propagation actually enables dead code elimination. So there's a little example there where we have an assignment to the variable a of the constant 4, and that value is actually used in a subsequent test. And if we actually constant propagate that value, we can perform the test at compile time and therefore eliminate it. Okay? So here's one example where if I do the one transformation, constant propagation, I can do another, which hopefully will lead to better performance. I've eliminated a test. However, things don't always wind up being cooperative, as we know. So transformations can also be opposing, or the opposite of each other. So here's an example where we've got a loop nest with two statements in it. And if I perform the loop distribution transformation, we split that up into two separate loops, each of which have a single statement in it. And we can also go back by performing the dual transformation loop fusion. So in this case, we might want to do one transformation or the other depending on the particular circumstances. So for instance, and we'll see an example of this as we continue, but for instance, a reason for liking the code on the left is there's less loop overhead. A reason for liking the code on the right is you may have fewer live registers. And finally, transformations can also interfere with each other. Okay, so for instance, instruction scheduling interferes with register allocation. So if you take that little piece of code on the left where you've got a computation on A and a computation on B, if we actually schedule those using separate names, A and B, then in fact we can get parallelism. They can be run in parallel. However, we wouldn't get a reuse of register names if in fact we use separate names. On the other hand, if we use the same name as in the code on the right, where we've just used R1, we wouldn't be able to run those in parallel, although we do get good reuse of registers. And in fact, there's been work for these two particular transformations trying to integrate them. Some of the work has been done by, for example, Cindy Norris and Laurie Pollock, who actually tried to estimate the number of spills that a particular schedule will get you. And then some other work by David Bradley and Susan Eggers and Robert Henry actually does instruction scheduling twice, the first time to get an estimate for register allocation. So now we've been in the world of theory, and this is these kinds of things are more, the folklore, what everybody knows about transformations. What happens in practice? Well, in practice, what's built into a compiler is a particular order of particular transformations. There can be repeats of the transformations, but in general, when you're building a real compiler, you pick some order and hold to it. And some kind of orders make perfect sense. For instance, we saw that constant propagation enabled dead code elimination. So in general, you'd want to put constant propagation before dead code elimination in this order. In fact, there's been some very nice theory about this. This is a work of Debbie Whitfield and Mary Lou Sofa, who suggested a partial order for transformations based on their enabling and disabling properties. So for instance, you see in this suggested partial order that constant propagation indeed comes before dead code elimination, which comes before code motion, which comes before loop fusion. Now, there are a couple of things to notice about this picture. One thing is that it's only got common transformations in it. Doesn't include everything, and people are always inventing new transformations, so there's room in this to add things in this picture. The other thing is that there are loops here. So in fact, that means you might want to do transformations more than once. And in practice, compilers don't loop on a transformation to see how many times it needs to be done. So in fact, some choice is made to how many times to do a transformation. And the other thing is this is just a partial order. It's not a total order. So in fact, judicious choice is still going to be needed in the general case. So now we're back to practice to see where we make these judicious choices in terms of writing optimizing compilers. And what's often done is to take separate architectural features. Okay, we've got parallelism, or we've got cache, and we want to have good cache locality. And to take those architectural features and optimize separately for each of those features. Okay, so it's a kind of divide and conquer strategy. Separate this complex problem into simpler, less complicated problems. And the way that that's done is by formulating an optimization problem which uses independent cost functions, where by independent here I mean just using the parameters of that architectural feature. So for instance, you might just use the parameters of cache to optimize for cache. And so when we start getting into this area, there's a question of how do we order these. So two examples where people have made opposite choices. In the Swift compiler that was developed by Monica Lamb and her students, they took the architectural feature of parallelism, in particular multiprocessor parallelism, and said, let's do that first, and then work on locality. And those two were done separately. Whereas in the work of Catherine McKinley, she decided to do locality first and then do parallelism. So definitely there's some choice involved here. And there in fact has been this, traditionally, this separation into different problems. So the other thing is that machines are evolving over time, and compilers are expensive to develop. So another trend has been to use single compiler for multiple architectures. And in this case, one certainly needs architecture-based guidance, because if machines can differ, you want your choices to be able to differ. So for example, if we go back to our loop fusion, loop distribution, those opposing transformations, if we have the architectural feature of coarse-grained parallelism, then we might want very big loops, very big parallel loops, so we might want to use loop fusion to get there. On the other hand, if we have vector processors, and we want to generate vector statements, we might actually want to distribute the loops over the statements so we can turn those statements, hopefully, into vector statements. So here's a case where architectural features would guide us to do different things. So now we've gone one full round from theory to practice. Why aren't we done? Well, there's a problem with practice. And the problem is how machines are evolving. The machines are evolving towards deep memory hierarchies, so not multiple caches, disks, memory, registers, etc., as well as multiple levels of parallelism. We're seeing multiprocessors with multiple functional units, etc. And then one wants to take those and build clusters and so on up. So why is this a problem? The problem is that these multiple levels of parallelism, multiple levels of memory, can create multiple bottlenecks. And just to codify that, one can say that there's a Murphy's law governing memory hierarchies, which is that these hierarchical bottlenecks actually interact. And so this nice way of approaching the optimization problem to say that let's divide it up and treat each architectural feature separately isn't enough in the case of these hierarchical bottlenecks. So this problem with practice is now going to take us back to theory and to develop new theory in order to be able to handle this. So to do that, I actually have to tell you, I'm going to use as an example our own work in tiling, and so I have to tell you about tiling. But this is easy stuff. Okay? So in tiling, you start from a loop nest, as in the upper left corner. And one operates to do the tiling on a graph, which is in the upper right corner, the iteration space graph. Okay? And there's a node there for every iteration of the loop nest. And the edges between the nodes indicate data dependencies between the iterations. Okay, so that's our starting point. In the lower left is an example of a tiling. Okay, what we've done is partitioned this iteration space into regular size and shape pieces with the idea that these pieces are now executed atomically. So we're actually changing the execution order by doing this tiling. Now let's see, there's several things to notice about this. One is that I've actually drawn parallelogram shapes. You're allowed to draw parallelogram shapes in this game. Okay? So they're not just rectangles or triangles. Another thing is I said these were regular shaped pieces, but that's not true around the border, but that's okay too, you're allowed that. The other thing is, by putting these tiles in place, we've actually made some of the edges be interior to the tiles. Okay? Now, if you're doing tiling, there are several reasons that you might do tiling. One is for locality, okay? To decide a size that actually fits in cache and execute that atomically. So interior edges would be good in that case, because that would indicate that you could keep those values, say, in cache. Okay. But there are also edges that are exterior to tiles, and those we call tile dependencies, because they're actually dependencies between the tiles, and they actually govern the order in which we're allowed to execute the tiles. So what we're going to look at actually here first is, in looking at how tiling transformations interact, is to look at how tiling can get used for parallelism. And it's really easy, as indicated by the lower right picture. What we're going to do is take stacks of tiles and farm them out to different processors. And we're going to have as many processors as stacks. Okay, so the first processor is going to take the entire first stack, and the second processor the next stack. Well, I showed you one example of tiling, but there are lots of ways we could have chosen to tile that example, each of which would be legal. Now, what do I mean by legal? I mean that there's no cycle of dependencies between the tiles. Why would that be bad? Well, a cycle of dependencies would indicate that you couldn't do any, you couldn't find a possible schedule that will satisfy the dependencies, so it would be thrown out. We couldn't really use it. But these are all examples of legal tile shapes. Okay, and notice that they look somewhat different. Why are we thinking about these at all? Well, what I want to show you is that these different shapes actually give rise to very different parallel execution times. So, for instance, if we take a look at the upper left example in the tiling that we have, the very first processor can start its tile immediately, but the second processor can't start its stack until the first two tiles are completed in the first stack. And the numbers that I've indicated here are the earliest finishing times of these tiles, given the dependencies, assuming that a full tile takes one time unit. Okay? So if we actually follow through and figure out this earliest finishing time, we get for this first left-hand example the execution time of 14. Now, if we look just to the right, that's a slightly better example. And there, the first processor can start its full tile immediately. But then at the next time unit, the second processor can start immediately, as well as the first processor continuing on its next tile. So what's happening is we're getting a kind of wavefront of parallelism in terms of the execution. And that's giving us a better execution time for this shape as comparing 9 with 14. But the best example here is the last one, because in that last example, all of the processors can start immediately. There's no startup overhead for any of them. And so they all start immediately and proceed in lockstep, and so we get a parallel execution time of 4. Okay. So what we have found is that different choices of these shapes can actually give you very different parallel execution times because of the startup costs. Okay? And my student, Karen Hogstead, has in fact been studying this problem and with the point of view of using it to guide choices of tiling for parallelism. Okay? But now, let's see. Now, let's see. I just want to illustrate this point a little bit further by giving you an idea why these different execution times arise. And the reason that this happens is that because of these tile dependencies, we actually get different critical paths for each of these examples, and they have very different lengths. And it's the critical path which is actually determining these execution times. So you can see for the left-hand example, it has a very long critical path. For the upper right example, it's a little bit better, but the best one is the bottom one. Okay? And that's really what's giving you these better execution times. Okay, so that was the brief introduction to tiling. Now you're all experts. And what I'd like to do now is just illustrate some of these points about transformations using tiling. And in particular, we're going to go back to the issue of how transformations interact. And one architectural scenario that's become increasingly common is having two levels of parallelism. For instance, the workstation on your desk may have multiprocessing capabilities, and each processor may have multiple functional units, etc. Okay. So the interesting thing about tiling for multiple levels is that when you take an iteration space and choose a tile shape and size, that tile becomes the iteration space for the next level that you're tiling. Okay, so there's a lot of control involved, and in fact, a lot of freedom in choosing the tilings for these different levels of parallelism. And in fact, one might want to, and we have, we can show you how this works, that you may actually want to choose to make a non-optimal choice at one level of parallelism so that you can get a better choice at the other level of parallelism. That is, we can actually trade off the startup costs by making these choices of the tile shapes. And the other point to make here is that there's really no right order. We can't say, well, you know, if you always do this bottom up, it works fine, or if you always do this top down, it works fine. The level at which you want to actually do the trade-off is problem and architecture dependent. And so there's really no right order here. You really have to look at the characteristics of both levels at once. The other architectural scenario that I want to tell you about is having both a TLB and a cache in a machine. Okay, so the as we were talking about thin and fat, TLBs are tall and thin. That is, there are TLBs have very large pages but have very few of them, so they're tall and thin. And caches are fat. They have many cache lines, but they're generally small, certainly compared to page sizes. And what happens if you're trying to tile for both TLB and cache is that you're being pulled in two different directions. The TLB is saying, pick a tile like me, and the cache is saying, pick a tile that looks like me. So these different shapes of TLB and cache are actually lead us to very different choices of tile shapes. And the example I wanted to just show you is the matrix multiply, the traditional example. And so what we've got in the lower left corner is the iteration space graph for matrix multiply. It's a triply nested loop, so it's three-dimensional iteration space. And what we're going to look at is choosing the height and width of that most deeply shaded block or tile. And we're going to look at strategies for doing that. Now, the way that we're going to do that is by constructing a cost function for both TLB and cache. And just very quickly, the way that we actually do that is by basically using counting arguments as to how many misses can occur in a particular tile. So what we're going to do is contrast using single-level cost functions, where we're going to use a cost function for cache only, or a cost function for TLB only, versus using a multi-level cost function. And you can see that in these cost functions, what we're doing is multiplying the miss count by the miss cost. And the miss count actually depends on the tile height and width. The multi-level function, in contrast, what we're going to do is put in the factor both for TLB and for cache And what that's going to allow us to do in optimizing this problem is actually to trade off the relative costs of TLB and cache by doing a single optimization. Okay, so here's the contest. We're going to start off first with a strategy where we say, okay, let's optimize for TLB first and then for cache. That's represented by the left-hand choices. So if we actually take the single level cost function, put in the TLB parameters, and grind out an answer, we get a height and width that's very long and thin, looks a lot like you expect TLBs to look like. So we get these an 800 by 20 height and width. But what happens when we do that, just looking at TLB, is that if we run that program with this tiling, cache thrashes terribly. Okay? This is not a good choice for cache. So then we go back and say, okay, well, how can we cut this down to make this acceptable and get both good TLB and cache performance? So we do another optimization problem, but here we're just allowing ourselves to cut down the height. And so in that case, we get a 297 by 20. Okay, so that was one strategy. The second strategy we're going to look at in this game here is to first look at cache, okay, and optimize with a single level cost function just for cache. And if we do that, we wind up choosing in this second column this very square tile. Okay? And square tiles have a good computation to communication ratio. And so when you don't have odd-looking modules like TLBs are, you often get square tiles. So, so we choose that size tile, but then we find that that doesn't have very good cache performance. So what we then do is reduce the width of that, in this case, because remember, TLVs were very skinny, so we have to reduce the width of that, hoping to get good performance for TLB. And again, we do that by a second optimization problem, but just looking at the TLB parameters. So what we would expect to be the best solution is using our multi-level cost function, which is the in-concert strategy. Okay, there we solve a single optimization problem, but we're using the parameters of both levels of TLB and cache. Okay, and the winner is, okay, so not so surprisingly, maybe, but at least here verified by simulation results. What we have here are the three different optimization strategies, the TLB first, cache first, and in concert. The green corresponds to cache and the blue to TLB, and the axis is, the y-axis is access times. Okay. And so what you can see here is that the last strategy is the best. Okay, and so this is what we expected, and in fact, it's verified by these results. The other interesting thing, though, is that if you take a look at that last column, and you look at how many, what the cost of TLB is, it's actually better than the TLB first strategy. And similarly, if you look at what the cache cost is in that last column, it's actually better than the doing cache first strategy. And that's because, remember, even though we optimized in those separate strategies, say the first one, we optimized for TLB first and got this optimal choice for TLB, we were forced to cut it down in order to get good performance for the cache. So it isn't the best for TLB anymore. So in summary, I hope I've convinced you that, in fact, theory and practice really should be going along together and influencing each other as we proceed. What I've shown you is that we started from this well-known theory that transformations interact, and that has led to a particular practice of building compilers where you use independent cost functions for different architectural features. But then architectural complexity in the form of new machines is introduced, and that gives us multiple bottlenecks, which force us to go back and develop some new theory, namely that we have to consider trade-offs with these multi-level cost functions. And that's where we're at now. We're in the process of actually translating this into practice and actually building a guidance system that takes this into account. Thank you.
you had a very elaborate discussion of TLB and cache. How about a super-scalar multiple issue compiler scheduling that is done versus tiling? Have you done any work on that? Or?
So that was a super-scalar?
Yeah, see, compiler optimization is done, for aiding multiple issue and super-scalar working, that's at the next level.
So I didn't talk about it, but another architectural scenario which has the same kind of multiple bottleneck problem is the case of, let's say, multiple functional units with the same shared cache. Okay. You get the same sort of problem, and there you're trading off ILP and locality.
Okay. Have you done any work on that, or is there anybody doing it, do you know? Or?
Well, yeah, we are looking at those trade-offs, yes.
Okay. And second question is, what did you use for simulation for those numbers? What package did you use for simulation?
Actually, we wrote our own cache simulator. I should have said a little bit more about the numbers. The parameters that we used for that particular simulation were basically MIPS R10,000 parameters, except it was a fully associative cache. Okay, we assumed full associativity.
So you wrote your own simulator or something? It's not a standard simulator?
No, no.
Anne Runge, hi. How much of this work is going back to your terms, theory versus practical application? In other words, are you just working toward publishing the theories of the best ways to put compilers together, or are you actually going to be generating a compiler?
No, we actually hope to actually build a guidance system which takes these into account. Yeah, so we are in the course of building a compiler. Or I should say a transformation system, since it'll be source to source.
Okay, and how are you handling the trade-offs between, you may be compiling for exactly the same processor, but in entirely different situations. For example, if you have a 486 that's based on a desktop PC, the user may want to optimize one way, versus if they have that same processor in an embedded situation, they may wish to optimize a different way. Are you taking that into account somehow?
So what we're actually using is a parameterized model in our system to help guide us. That model is actually going to be based on both the particular machine, so the machine architectural parameters, as well as on the needs of the application. Now, we haven't really thought about different levels or different purposes in doing optimization, but that's a very good question, because in fact, if you have a handheld device, you have very different needs than, if you've got a fat PC. So we haven't been taking that into account, but it's certainly something that will be. One of the future directions of this work is to look at heterogeneous computing platforms and to have the same goals here as we have in the homogeneous world. And I think there are a lot of interesting issues there.